There exist weaknesses in the current framework that is in place in order to estimate water mass characteristics, and this study represents our replacement to this framework using from a material approach. The outline of the presentation is the following. What motivated this study, and why is it so important to understand these convective processes with such high resolution datasets, as well as what this traditional framework in place actually is, and why we would need to update the framework in order for it to be efficiently used, as well as an explanation of what our update is and some of the technicalities in applying this methodology, as well as a showcase of some preliminary results and future works and next steps we can make. Dense water is formed at specific locations throughout the oceans, and they have been linked to the renewal of nutrients within the upper layers of the ocean, as well as the sequestration of anthropogenic greenhouse gases. They occur normally in areas of cyclonic gyres, as you can see from the schematic on the right, which acts to bow up isopycnals, weakening vertical static stability in the water column. This sets up the conditions in which air sea heat fluxes can cause vigorous convection, sometimes to the base, through to the ocean bottom. Once the water column here starts to re-stratify, then this convected water is enclosed within the ocean interior, carrying with it a memory of the conditions which led to the vigorous convection. Normally, literature has used in situ model data to estimate this effect. However, you would need very high temporal resolution data, as these events only take place from about a few weeks to a month. But the framework that is in place to estimate these events are not very suited to take these high resolution data as inputs. What exactly is this framework? And it was coined in 1982 to connect interior circulation effects to air sea heat fluxes, thereby connecting the interior of the ocean to a knowledge of only surface variables. How this works is that heat and fresh water act to force temperature and salinity changes at the surface of the ocean, and by the relation of temperature and salinity on density, you will then get an equivalent flux of density through the air-sea interface. There are a number of assumptions which go into this framework, in that the forcings, the air-sea heat fluxes, are uniform over the whole mixed layer, meaning that the density flux would then become a mass flux through the ocean surface integrated over the mixed layer. And assuming that assuming conservation of volume, these density fluxes can only happen with a diapycnal volume transport, and integrating these density fluxes over the area of the isopycnal, as you can see on the figure on the upper right, you will get an estimate of this diapycnal volume transport. Now, due to the fact that there is differential heating at the ocean surface, you would get a differential in this diapycnal volume transport, whose convergence and divergence would lead to an estimate of the fluid transfer through the base of the mixed layer. The weakness of this framework, the inability to be applied to high resolution datasets, is that this framework depends upon air-sea heat fluxes, which is a problematic field in their estimation. For example, in situ based datasets are heavily biased to areas of repeat observations, and areas of sparse observations are relatively highly uncertain, as you can see by the figure in the upper right. On the figure in the lower right, what you see is into comparison between 12 modeled datasets against in situ observations throughout the northern hemisphere. Modeled and satellite datasets improve upon this issue of sparse observations drastically. However, looking at the figure in the lower right, you will see that in areas of lower wind speed, you see that there is a relatively good agreement between both approaches. However, as wind speeds rise, then due to an uncertainty in the estimation of some atmospheric state variables needed to be applied in order to be ingested into formulas used to estimate these fluxes, you have a very high divergence. And these areas of high wind speeds are areas such as the western boundary currents as well as around the Southern Ocean. Our update stems from the fact that if you take the conservation equation for a tracer property, as you can see in the upper left equation, you can decompose it into a term called, which is the mixing caused variation in the scalar property, as well as a forcing on that scalar property. Now, if you take the material changes of temperature and salinity, as you can see by the two equations in the lower left, then you can equate them to forcings ignoring mixing, and these forcings would then be the heat and freshwater forcings that are taken into account in the air-sea flux approach. And by taking the relative influences again of temperature and salinity on density, you arrive at an equivalent equation between density flux of a material approach and of this air-sea flux approach, as you can see on the equations on the right. However, in order to reconcile the conventions that each of the equations are referred to, as in the traditional air-sea flux, the air-sea density flux is an integration of all forcings over the mixed layer, we would need to multiply our approach using the material derivatives over the mixed layer. As well as this, we would need currents and of course mixed layer data in order to compute the material derivatives. Some of the issues that were evident when we were applying this methodology is that due to the way that we approach, we estimate, numerically derive the time, Eulerian partial time derivative needed for the material derivative, is that it had the effect of shifting all temporal grids forward by half a time step. And to resolve this, we would need to average all results over 2 time steps to get a half shifted time grid. And this comprises a summary of our approach. And some of the results are presented here, where you can see on the left column you have the air-sea density flux, and on the middle column you have the material density flux, which is from our approach, and you have the difference on the left column. The most striking difference you can see is this area of high underestimation shown by the blue, and these data, this is from model data taken annually averaged over the year 2013. This area of high underestimation circumventing the Southern Ocean, as you can see by the bottom panel in the middle column, can be broken down into a buoyancy gain in terms of temperature, as you can see by the thermal contribution to the density flux in the middle panel of the center column, and a buoyancy loss and a density gain through freshwater forcings on salinity, as you can see by the upper panel in the middle column. However, in order to put these results into context and to compare both approaches, we would need to see if this signal has been observed in literature, because it is completely absent in the air-sea flux approach. And indeed, literature has cited that the meridional circulation within the Southern Ocean can be summarized in terms of a deconsal, where high winds create a northward Ekman transport at the area of the polar front, which is approximately the area of the polar front. And this northward transport causes the upper circumpolar deep water to upwell, and this is mainly seen in the Indian Ocean sector of the Southern Ocean, which is exactly what you can see by the ellipses which enclose the areas of underestimation and overestimation shown by the mid-latitudes downwelling of water to complete the cell. However, this is completely unresolved with the air-sea fluxes, which are normally caused, as I mentioned, by high wind speeds that exist around the Southern Ocean. The future work would be that we are already preparing a paper, but we need to analyze and we need to assess the quality of our approach against the traditional approach, as well as then applying this methodology to summarize and to understand certain areas, especially areas of meridional overturning circulation, which have been shown to be areas which could be a weakening of this circulation. As well as that, we need to assess the added advantage of using satellites, as was our initial aim, in order to compare it with the model output to see its added advantage. And that represents the end of my presentation, and here are the references.